Okay, now we're observing the system, the same collision, but observing it from a new coordinate system. New coordinate system is moving at 3 meters per second with respect to this one. Now, if you're moving at 3 meters per second next to something that's moving at 4 meters per second, then that something moving at 4 meters per second appears within your coordinate system, would be measured within your coordinate system. If you're measuring its speed with electronic instrumentation, let's say, its speed would be 1 meter per second. Okay? If somebody's putting along in a car at 4 meters per second and you're putting along in your coordinate system at 3 meters per second, maybe in the adjacent lane, they appear to be moving 1 meter per second faster than you are. Well, they are moving 1 meter per second faster than you are. If you're measuring their speed with accurate instrumentation, you're going to measure their speed as 1 meter per second. You're not on the road. You're not measuring with instruments that are sitting on the road. You're measuring with instruments that are moving with you. And you're going to measure this speed to be 1 meter per second. Okay, what are you going to see on this speed? Well, in this case, you're moving along at 4 meters per second. This thing's approaching you at 2 meters per second. Okay, it's going to appear to be moving in what you perceive as the negative direction, assuming your positive direction agrees with the positive direction we've used here. You're going to perceive that as moving at 3 meters per second faster, at 5 meters per second toward you. So its speed is going to be negative 5 meters per second. Now, what's the sum of the momenta here? Well, it's really easy to calculate. I'm using v hat and u hat for the velocities before and the velocities after, and I'm putting the hat on to distinguish the velocities from the velocities here, because after all, we're measuring the same objects. We're measuring the same system, we're just measuring it from a new coordinate system. It's moving with respect to the old one. Okay, so in the new system, we find that the sum of the momenta, the sum of the MV contributions here, is negative 0.9 kilogram meters per second. Very easily calculated. 100 grams times 1 meter per second is 0.1 kilogram meter per second. 200 grams times negative 5 meters per second is negative 1 kilogram meter per second. That adds up to negative 0.9 kilogram meters per second. Now, the kinetic energy, and I messed this up in class. I got messed up here on my decimal points. The kinetic energy of this object, if we square 1 meter per second, we get 1 meter squared per second squared. Take half of this mass, well, this mass times 1 meter squared per second squared is going to be 0.1 kilogram meter per second squared, and half of that's 0.05 kilogram meters per second squared, or 0.05 joules. Now here's where I kind of messed up, but if you square 5 meters per second, get 25 meters per second. Multiply that by 0.2 kilograms, you get 5 kilogram meters per second, meters squared per second squared. I'm not saying the unit's right. And half of that is 2.5 kilogram meters squared per second squared, or 2.5 joules. So now you got 2.5 joules here. You add that to the 0.05 that you have for the first object, and you've got 2.55 joules. Okay, now here we do our masses and velocities, and we add up mv1 plus m1v1 plus m2v2, and we get the same thing we got before, and you should verify that. It's a very straightforward calculation. Just multiply this by 100 kilograms, this by 200 kilograms, and you're going to get negative 0.9 kilogram meters per second. And I might have said kilograms, these are in grams of course, so you'd multiply by 0.1 kilograms and 0.2 kilograms. Okay, calculating the kinetic energies, if we square 7 meters per second, we get 49 meters squared per second squared. Multiply that by 1/10 of a kilogram, we have 4.9 kilogram meters squared per second squared. Take half of that, and we get 2.45 kilogram meters squared per second squared, or 2.45 joules. Okay, do the same thing here. Square this, we get 1 meter squared per second squared. Multiply by 0.2 kilograms, we have 0.2 kilogram meter squared per second squared. Take half of that, we have 0.1 kilogram meters squared per second squared, which is 0.1 joule, and that adds up to 2.55 joules. No question mark over here now. And this agrees with this. So we see there's no change in kinetic energy, but we also see that the kinetic energy is greater than it was over here. Okay? Now, it makes sense that the kinetic energy would not be the same in different reference frames, as measured from different reference frames. If you were moving past this thing at 100 meters per second, then you'd have very big velocities here. You'd have negative 96 meters per second here, and you'd have negative 102 meters per second here. Square those, multiply by the mass, take 1/2, you're going to get much bigger kinetic energies. So the kinetic energy really depends on the system, and so does the total momentum of the system. Now there's more I could say about that. We're in the center of mass frame here. If you multiply the total mass by the velocity of the center of mass frame, you're going to get this. The velocity of the center of mass frame is measured from the new system. That's more than you really want to think about right now, but that's what we have. But since I talked about the center of mass frame, I want to come back and talk about what I mean by the center of mass frame. Now we're talking about it somewhat loosely right now because we haven't done center of mass, and unfortunately most of the class seems to have gotten out of high school without knowing anything about center of mass. I find that a little bit incomprehensible until I think about the other things that I see, and I find that, yeah, okay, it makes perfect sense. Shouldn't be that way, but I understand that it is. Okay, so we'll come back and talk about center of mass frame briefly.